Hello everyone, my name is Mohamed Walid, ID 46-4429 T50, and I'm going to illustrate how the car moves along the track using infrared sensors. The car uses two infrared sensors connected to a 5-volt source from the FPGA and a common ground. The sensors can use digital and analog output, but we chose to use digital output. If the sensors detect a reflective source, the green light will turn on and the car will move forward. If both detect a non-reflective surface, the green light will turn off and the car will stop. If one sensor detects a non-reflective surface, the car will turn in that direction, like so.
Hello, this is Ali Amr 46-MET T18. I'm going to explain the ultrasonic sensor. The sensor consists of 4 pins. The first pin is VCC, which is connected to a 5-volt source. The second pin is ground, which is connected to the common ground. The third and fourth pin are trigger and echo, which are initially 0. The trigger is set to 1 for 10 microseconds, and then it sends 8 pulses of ultrasonic waves. When these pulses hit the surface, they got reflected, and once the first pulse is received, the echo is set to 1 until the 8th pulse is received. Then we can calculate the time between sending and receiving, and then we are able to calculate the distance. And if this distance lies between a specific range of distances, the car will stop.
Okay. Hello, this is Mohamed Zakaria, T48, 46-6182. Today I'll be discussing the motors for the car project. Okay. So first of all, we have 4.5 brushless gear motors. Okay. Since we don't care about the polarities of the motors, they can be arranged in any way. However, the arrangement has to be maintained for all motors. However, you can see that they're different in some of them since they're just flipped. But if you keep them in the same alignment, you're gonna find that they're in the same arrangement. Okay. Here we'll be discussing the H-bridge, which is the most important component for the motors to move. So the H-bridge has a VCC input, which is connected to 6 AA batteries, and the ground input is connected to the common ground of the car. Okay, so here we have 6 pins. These input pins, they are the enable input 1 and input 2 for each of the motors. The H-bridge can control 2 motors. However, we only need 1 H-bridge since motors on the same side, they're going to be moving in the same way. So we only need 1 H-bridge, not 2. Here we have the enable input 1, input 2 for the first motor, and input 1, input 2, and the enable of the second motor set. So if the input 1 and input 2, if they're both 0, 0 or 1, 1, the car is not going to move. However, if it's 1, 0, the motors are going to start rotating in a certain direction, and if they're the opposite, 0, 1, they're going to start moving in the opposite direction. Here we have the VCC and the ground that are going out to the motors. This one's for this side and this one's for the other side.
Hello, my name is Ismail Shinnawy. I'm 46-4847. I'll be tutorial 48. I'll be walking you through a short demo of our project, and then the VHDL code that's responsible for running the logic for the project. If you look over here, this is the car, the FPGA board. Currently the code is already uploaded on the board, but the car isn't moving because there's an obstacle in front of it, and the ultrasonic sensor is detecting it, so it stops the motor. Now if I remove the obstacle, it will start to move and follow this path until the other obstacle, at which it will stop. So over here, if I remove this obstacle, it will start to move again. And as you can see, it followed this path. There was a curve over here, and it followed it. And now it stops because it detects another obstacle. That's it, and thank you. Hello, my name is Ismail Shinnawy. My ID is 46-4847. I'm from tutorial 48. I'll be showing you the VHDL code we use in this project. The code consists of two parts, the entity and the architecture. The entity consists of 3 inputs and 3 outputs. The inputs are a clock FPGA, which is an STT logic input. It comes from the FPGA clock that is supplied by the FPGA board. It's a 50 megahertz clock. And we have the echo, which is an STD logic input. It is supplied by the ultrasonic module on the echo pin. We have a line follower, which is an STD logic vector of length 2. It's supplied by the 2 digital pins on the infrared module. We have also the 3 outputs. The first output is an STD logic output, which is kill motors. It's just an LED to indicate that we stop the motors. We have also a trigger, which is an STD logic output. It is supplied to the ultrasonic module on the trigger pin, and we have motor A and motor B, which are 2 control signals, each of length 3, an STD logic vector of length 3, which is supplied to the H bridge to control its functionality. So this is the entity. For the architecture part of the code, we have a signal, which is the echo time, which of type integer, which represents the number of pulses that passed while the echo input was set to high. We have a process with a sensitivity list consisting only of the clock FPGA. Within the process, we have 3 process variables, which are C1, C2, and F. C1 and C2 are of type integer, and we start them off with the value of 0. C1 represents a counter for the trigger, which represents the number of pulses that passed while the trigger was set to high. C2 is also of type integer, and it represents a counter for the echo, which represents the number of pulses that passed while the echo was set to high. The flag is just the F is just a flag that is used with the ultrasonic logic. So first of all, we check if this is a rising edge of the clock, and then we have the logic for the line follower, which is explained by my colleague Mohamed Walid. As he explained, we have 4K. This is a line follower is a STD logic vector of length 2. So we have 4 cases: 0, 0, 0, 1, 1, 0, and 1, 1. For each case, we set the controls that are sent to the H bridge as we want. For the ultrasonic logic, it follows the same explanation that my colleague Amr said in the video. First of all, we check if the C1, which is the trigger counter, is 0, which means that this is the first time we started this process, and then we set the trigger to 1. If the C1 counts 500 pulses, this means that 10 microseconds has passed, because the frequency of the input clock is 50 megahertz. So we set the trigger to 0 and set the flag to 1. If C1 counts 5 million pulses, which means that 100 milliseconds passed, then there is no obstacle in front of us, so we start the process all over, and then we increment the counter. For the echo logic, we check if the echo signal is set to 1. Then we increment the counter, the C2 counter, which is the counter for the echo. Else, if the echo is set to 0 and the flag is set to 1, then we save the value of C2 in the echo time and reset both the C2 and the F. Then we check if the echo time is less than 100,000 pulses, which means which corresponds to 2 milliseconds. Then using a speed distance time triangle, we can calculate that an obstacle is ahead 30 centimeters. So we kill the motors by setting, of course, by setting the LED to high, and setting the motor A and motor B to all zeros to kill the motors. Else, if it's not less than 100,000 pulses, then we don't kill the motors and leave them as they were set here. This is it. This is the code for our project.